Okay.
So are we on live streaming?
No, not yet.
Yeah, I started just now.
Okay. Okay, thanks, Vignesh. Okay, let me share my screen. Okay. So, is my screen visible to everyone? Abhinandan, can you respond?
Yes, yes.
Okay, thank you. Okay, so in this week activity and practice session, we are going to look at the week 3 of machine learning foundations. So let us begin with our first week video, which is the lecture on 4 fundamental subspaces. So our first activity question here is here. So we represent the column space of A and row space of A, null space of A as follows: C of A, R of A, and N of A. So the first question is, which of the following are true about the column space of matrix A? So if you consider the column space of matrix, so it is the linear combinations of the column vectors of the matrix A. See, for example, let me show you an application. It's not loading. So if you see here, so this is a simple applet which shows you 2 columns of matrix. So this is an matrix A. So in this matrix, there are 2 columns with 1, 4, 2 and 0, 3, 3. So for this column, for this matrix, we have the column spaces, the linear combinations of these 2 columns. So this B is a linear combination of this column. So this is a linear combination. It's any multiplication of any scalar gives you a space. So this B vector, this also lies in the column space of this matrix. So let's return to the question. So the column space of matrix A consists of the linear combinations of the column vectors of the matrix A. And it is the span of the column vectors of A. So if you consider A transpose, it leads to the row space of the matrix. So the second question, if X and Y belong to the null space of A, then the linear combinations of X and Y also belong to the null space of A. So this you must be able to answer from the previous question itself, because if in the space, the linear combinations will also be in the space. Okay. So Venu Madhav has raised his hand.
Ma'am, I have a question I can ask now.
Yeah, you can ask now.
Ma'am, it is written as the column space of a matrix is the linear combination of column vectors, right? So what I see is a matrix is reduced to reduced row echelon form, and from there we see the number of pivot columns.
Yes.
If the matrix is like 3 by 5 and the number of pivot columns are only 2, you pick those first two columns, maybe first 2 columns are the pivot columns, and span of those is the column space, right? But not the span of or linear combination of all the column vectors of that matrix. So how could that be correct option?
See, if you consider the matrix A, no, so if corresponding columns with respect to the pivot, what happens? The other columns are also the combinations of the pivot columns. They are dependent on these 2 pivot columns. So in that sense, we are telling that it consists of the linear combinations of the column vectors of A. Anyhow, it consists of the pivot columns, which means the other columns which are dependent on those pivot columns are also in this space.
Okay, that means the other columns are some kind of linear combination
So of
Of
the pivot columns.
Pivot columns. Okay, got it, ma'am.
Yeah, that's why we tell like that. Okay.
Thank you, ma'am.
Okay, thank you. So based on this first observation, we can also say that any linear combination of two vectors which belongs to the null space of A, which also will be in the null space of A. So this is also true here. For the third question, so which of the following is true about the null space of matrix A? So we have already seen in the lectures also, in order to be a vector in a null space of A, it has to give a zero vector when multiplied by the matrix A. So therefore, the null space consists of the solutions to Ax is equal to 0. So those vectors belong to the null space of the matrix A. So this gives the answer to the next question. That is, a vector x belongs to the null space of a matrix A if Ax is equal to 0. So that is why we call it as a null space. Because the matrix A consists of numbers, but when we are multiplying it with a vector, it gives us a zero vector, which is a null space. That's why it is termed as a null space. Okay. So when you, the next question is Gaussian elimination changes the null space of a matrix. Definitely it's not going to change the null space of the matrix, because when you are eliminating the rows or eliminating the rows of a matrix A, it is going to lead you to a reduced form. So which is again the form which has in the matrix A. So that's why this is not going to change your null space of the matrix. And the sixth question is, if a n cross n matrix A is invertible, then which of the following is or false? So what is an invertible matrix? So a matrix A is said to be invertible if it has an inverse. That is, A has a matrix, when multiplied with A, you get it in identity matrix, that is I. So therefore, A, consider for example, oops, sorry, I lost my screen.
It's visible now.
Okay. So I consider, so if you have a matrix A, then there exists a matrix B such that when you multiply this matrix, you get your identity matrix. So this B, we call it as our A inverse. So A into A inverse gives you a identity matrix. So this is the condition we say when we say that the matrix A is invertible. So how we can check whether a matrix is invertible or not? When the determinant of this matrix A is not equal to 0, at that time we can make sure that the inverse of the matrix exists, that is A is an invertible matrix. So such kind of invertible matrix, what happens? For those invertible matrix, your column space is fully in the n-dimensional subspace, that is R or N. So this is true, and this Ax equal to B has a unique solution. It does not have multiple solutions. It has a unique solution since it is invertible in nature. And the null space of A, that is the null space of an invertible matrix, contains only the zero vectors. So the only false condition is Ax equal to B has infinite solutions. It has a, because it has a unique solution. Okay. So which of the following is or true about M cross N matrix A? So for any matrix A, for example, let me write here. So if a matrix A has size M cross N, so which means there are M number of rows and N number of columns, right? Therefore, that should be in your R power N. So that is in an n-dimensional space. So when you get a row space of A, so this row space will be containing your rows. So it is in the subspace R power. Yeah, I think. And when you get your null space of A, sorry, column space of A is, it contains the number of rows, therefore it is N. So here it is N, right? See, for example, A11, A12, up to A1N. A21, A22 up to A to n. We have a matrix like this, and AM1, AM2, and we have an AMN. Okay. So in this matrix, so this is our column space which has the column vector. So therefore it is in m dimensional space. And here we have this rows, therefore it is in a n dimensional space. When you get the null space of it is in the rows of the matrix when are used for the null space computation, therefore it is R power n. And for null space, left null space, which is n of A transpose. So here it is in R power R of m. Okay. So the dimension of this column space is equal to m. So here the question is the dimensions of column space. So when you get the dimensions of column space, it is the rank of the matrix. That is the number of linearly independent columns. So that is equal to R. And the dimension of the null space of A is the nullity, which gives you n minus R. So therefore here it is R plus n minus R, that is equal to n. So this is your first correct option. And when your dimension of, so this is an alternate condition. So here it is R, here it is n minus R. So it is not equal to n. Therefore, this is a wrong option. And rank of A is R. Nullity of A is n minus R, which will give you n, but here it is m. So this is a wrong option. And this is the correct option. Whereas rank of A is R plus nullity is n minus R. So therefore, you will get n. And this dimension of C of A transpose. So column C of A transpose is what? It's your row space. So therefore, here you will get m minus R plus the dimension of n of A of t, which is your dimension of your left null space, that is m minus R. So we cancel it, R and R. So you will get your m here. So these three are the correct options. And the last option is wrong, which is the dimension of the row space is R, which is the rank, R plus. So here dimension of left null space, n minus R. So therefore you will get m here. Okay. So I hope you understood maybe some few notations. If you write it out, you will get the answer correctly. So based on the previous question, you can directly answer this question. So you have the following statements regarding the rank of a matrix. So rank of a matrix is equal to the dimension of its column space, which is also equal to the dimension of its row space. It is not equal to the dimension of null space, and it is not equal to the number of columns of the matrix. So this is your correct answer, 1 and 2. Okay. So in this 4 fundamental subspaces activity, do you have any questions?
No.
Ma'am?
Okay. Yes. If you have any questions, you can ask.
I have a question regarding this question number 6.
Okay. This question.
Yeah, question number 6. The thing is, I know what is when we say that A is invertible. So
Okay.
if you multiply the matrix A with its inverse, you get an identity matrix, and we say that A is invertible matrix.
Yes.
And from a reduced row echelon form, I can identify if the given system of solutions has a unique solution or infinite solutions, and so on. So
Yes.
these two things I'm there, but after I see the question, I go blank. I mean, I don't know how to correlate these two concepts I have in mind and answer this question.
Okay. What kind of correlation you mean? So if you have a matrix which is an invertible matrix, and if you find the column space, it is an n cross n matrix. Okay.
Yeah. So first option is fine because
Okay.
column space of A is also always subspace of R.
Rn.
N where n is the number of rows. Here
Yes.
rows is n, so that is also fine.
Fine. Okay.
Yeah. How to answer or analyze option number 2?
So how to answer option number 2? See, actually, how, let me tell you. Okay. See, if you have that matrix A, for example, let us consider a 3 cross 3 matrix. Okay. So in this matrix, so we have some values 1, 2, 3. This is for example. Let us consider this as an invertible matrix. Okay. So if you consider this matrix, so there are 3 cross 3 means 3 equations and 3 unknowns. Can you get me? So when we want to solve the system of equations, Ax is equal to B, what happens? We have this matrix multiplied with x1, x2, x3 and is equal to some b1, b2, b3. Am I correct? So we have this system of solutions. So this is where we explain how do we get the system of solutions. So we write this A matrix multiplied by this x1, x2, x3, which means we have 3 unknowns in 3 equations. So this is solvable, correct? When why we say it is infinite? When we have more number of unknowns, but lesser number of equations. Yeah. Hello?
So the way I conclude it has infinitely many solutions or not is I reduce this matrix into row reduced form, identify the number of
pivots, you will be
non-pivots or free
okay.
variables. I assign parameters R, S, T if there are 3 non-pivots, then express this x1, x2, x3 in a column matrix times R plus column matrix times S and plus column matrix times T. Then because there are 3 R, S and T, you can
we have that
input any number of, so yeah.
We have that special solution, right? XP and XS. When we solve that null space in the lecture, sir would have taught like that. How to arrive at the solutions. So this is the basic thing from where we can able to find the solutions. So if you have more number of unknowns, what will happen? There will be infinite solutions. So that from that is what I understood in writing this unique solution.
Yeah, another way is like whenever you see that it is invertible, that means it is a full rank matrix, right? So that means its null space is 0. So nullity is 0. So since it doesn't have a null space, you will always get a unique solution.
Null space contains 0 vector. Yeah.
Correct. So your nullity is basically 0, right? So since without the trivial solution, you will always get unique solution.
Yes, exactly, Rajiv.
Yes, ma'am, can I come in?
Yes.
Yeah, so I just extend to Rajiv's point.
Okay.
Basically, if there are no free variables, which is because there is no null space, free variable could take any value, and also because of that, other variables will take different values, right? So since free variables itself are not available, all the variables in that matrix will take just one value. That's unique value, I guess. Is it correct assessment?
Yeah, because we do not have free variables. We have only the pivot.
Because free can take any value, right? Free can take any value.
Free means we are free to select any values.
Right. So if they are not there, then obviously the others will take just one value.
Yes.
Right? Okay, thank you.
Okay. Okay, so shall we proceed? Okay.
Yes, ma'am.
Yes.
Okay. So in our second lecture, it is more about your orthogonality in vectors and the orthogonality of the subspaces. So as a first question, we have this length of a vector x. So in most of the cases, we assume our vector x to be in a column vector. So in that case, the length of the vector is simply your square root of the dot product of the transpose of the vector x with the vector x. So this is your option. Square root of x transpose x. So this is very straightforward. You would have learned it earlier in the earlier weeks also. So next question, two real vectors x and y are orthogonal. So why we call two vectors as orthogonal? When their dot product is equal to 0. So we arrive at the dot product with X transpose Y is equal to 0, or we can have it as Y transpose X is equal to 0. And the further notation is X dot Y is equal to 0 and Y dot X is equal to 0. So whenever we have that linearly independent relationship between any two vectors, they may be orthogonal. So if their dot product is 0, which also means they have a 90-degree angle between them. Okay. So which of the following vectors is orthogonal to any given vector? So this is also a straightforward question. So for any given vector, the 0 vector is going to be the orthogonal to that vector. Because when you multiply 0 with that of vector, you will get an answer as 0. So the dot product of the vector with the 0 vector is equal to 0. So therefore, the 0 vector is orthogonal to any given vector. So if, next question, if two vectors x1 and x2 are orthogonal, then they are not linearly independent. So this is a false statement, because the first condition is they have to be linearly independent. Then we are checking for the orthogonality.
And ma'am, here like the converse is not true, right?
No, yeah, converse is not true. Two vectors may be linearly independent, but they may not be orthogonal to each other.
Correct. So say
Yeah.
for example, whenever two vectors are there, okay, like,
Yeah.
just to check it whether they are linearly dependent or not. So if we can scale one vector and get the other vector, that's the only way, right?
Oh no, we have to write when two vectors are there, we have to take a linear combination, right?
Yeah, but
C1.
like you have only two vectors, right? Like how you
Yeah.
will take a linear combination and get another one? Because then you are using the second vector, right? So actually
Oh,
from
in that sense, okay.
yeah, so basically you have only two vectors, right? And you need to check whether they are linearly dependent or independent. Okay.
Independent, yeah.
So that time choose any one of that vector and scale it.
And you scale it, you can multiply with any by any factor.
Correct, correct.
If you get the vector in the same direction and with aligned with that of the other vector, then it is dependent on that vector.
Yeah,
If it is not, means it is independent of that vector.
correct, correct.
So, for example, you may have two vectors like this. For example, you take this as x and y. So here, so this x and y plane are orthogonal to each other. So if I plot any vector here, and if I plot a vector, say for example 2, 1, 3. So this vector is linearly independent on x, or it is dependent on x and is dependent on y.
Why?
Yeah. So how this vector is?
Yeah, 2 multiplied by 1 0 plus 3 multiplied by 0.
Yeah. So that's the case. So if we have two different vectors, say like this vector is here and this vector is in this direction. So this is in the negative direction, right? This is in positive x. So this is your y. So this is our negative y. And this is a negative x. So this vector here, it is never dependent on this vector. So this, for example, it may be 1, 5. This can be -5 or -5. So if you consider these two vectors, so these two vectors are linearly independent of each other. Because, but they are not orthogonal. Definitely they are not orthogonal.
Right. Yeah.
So that is the sense that you are referring to. So next question, two vectors x and y are orthonormal. So orthonormality calls for your orthogonality to be true. So the dot product of these two vectors has to be equal to 0. And in addition, their vectors has to be in unit length. So this is your option. So x dot y must be equal to 0. And the length of the vector x and the length of the vector y must be equal to 1. So two subspaces S1 and S2 are orthogonal. So far we tried relating the vectors. So now we are going to look at how the subspaces are going to be orthogonal. So how can we say that two subspaces are orthogonal? When every vector in the subspace S1 is orthogonal to every vector in the subspace S2. So that is this option, because for all the vectors, this is for all x and belongs to x1, and for all y that belongs to S2, their dot product should be equal to 0. It is not like for each x belongs to S1 or for each for all belongs to S. Some vectors are orthogonal or some vectors are not orthogonal also. We cannot say like that. Every vector must be orthogonal to every other vector. So that is the condition to say that the two subspaces are orthogonal or not. So only this option holds, the other options are false in that sense. So which of the following is are true? So the perpendicular symbol refers to the orthogonal complement of. So we have seen the big picture in the tutorial also. So your column space is an orthogonal complement of your left null space, and your row space is the orthogonal complement of the null space. So how we can say this? Let us see. Yeah, brief explanation. So consider the matrix A. So here we have a matrix A. So this is of size say m cross n. So you have the numbers, you can write it as 1, 0, 1, 0, something like that. So if you have this matrix A, so your column space of A consists of the rows which is in the dimension R per R of n dimensional subspace. So like we wrote earlier, and your row space is in the dimension R of m. So where did this null space comes from? Null space is also related to the solutions of the vectors which gives Ax is equal to 0. So when you solve that, you will get the vector x which is in the m dimensional subspace. So this is what you will get for null space of A. So similarly, for left null space, when you solve it, A transpose y is equal to 0. At that time, you will get y vector in the dimension of Rn. So this is your null space of A transpose.
Ma'am, can I come in?
Yeah, just a minute. So these two spaces here. So these two spaces are orthogonal complements, and these two spaces are orthogonal complements. Yes?
Ma'am, wouldn't column space be in Rm because m is the number of rows, right?
Correct. Rn. And here it is Rn. Okay.
Second, column space and row space, they are also orthogonal, right?
Column space and row space cannot be orthogonal because their vector dimension itself is different. No? The column space and row space. If you consider the vector size, for example, if you this is an n cross n matrix. So the vectors of column space of A, it is in here, no? It is in number of elements are
Yes,
equal
yes,
to
yes.
m. But
Yeah.
or it is number of elements is n.
Okay, say for example, if it is a m cross m matrix, okay.
Even if it is an m cross m matrix, so if you frame the column and row, so these columns and rows maybe for say identity matrix 1 1 1 1 1 1 likewise. For those
Yeah.
matrix even it is 1 1 1. Okay, only one row will be the answer for the column space. Spanned by it's a line through the ones vectors of ones. So that's a special case, no. Otherwise, if you
Say for example, it is not an identity matrix. It is a
Yeah.
like a matrix,
a normal matrix, okay.
normal matrix with m cross m dimension. Okay.
M cross M.
Right, square matrix.
Yeah, square matrix.
Correct. In that case, column space, null space is a subspace within the column space, right?
Null space is a subspace of column space.
Because see, like you have the column space.
Yeah.
That
No, null space is the solution vectors that gives you zero vector. How can they be in a column space?
no, okay. Think this A as a linear maps, right? It is sending like from vector space V to vector space U.
Okay.
Okay. Now the column space of A is basically representing something like column space of A is representing V, right?
So for example, you have a column space as there is a space
Yeah.
with vectors, okay, and another space V. Like this, you are telling, no? Space
Yes.
with
And say, for
vectors.
example, there is a map from U to V, and that map is represented by this A.
So I'm mapping this U to V with A.
Correct.
Okay.
So now column space of A represents what? U.
The column space of A represents the vectors, the span of the vectors of this column of this
No.
A
Column
matrix, which
space
is
of
U.
A is basically the V vector, V space, right? Because how we form this column like A, it is the like combination of those bases from the like a V.
Okay. So
Okay,
where does this null space of A fit in here?
so sorry.
Where does the null space come? Null space fits here. Null space of A.
See, like in my mind, say for example, if A is representing V,
Okay.
like column space of A is representing V.
Okay.
If it is, then my statement was wrong. But if column space of
Yeah.
A represents U, then null space is within that U itself, right? Because some U which are getting mapped to 0, that is the null space.
Some U which is getting mapped, no. Some vectors which help you to get U mapped to 0 is the null space.
Correct. So that means like this map A, okay.
Yeah.
When you have some vectors belongs to vector space U, which when transformed through this A will reside go to 0 in V, right? 0 belongs to V. That is the null space, right? Null space of A.
Okay. Now I got your point. See, if your vectors in V that gives you A, those vectors are producing a 0 vector. Then it has to be in a perpendicular direction to this space. No?
Perpendicular of what? Like perpendicular to V.
Yeah, because their product is equal to 0. The vectors are mapped to V. At the time, their products are
Okay.
equal to 0.
Understood.
Yeah.
Yes. It has to be perpendicular to V.
Yeah.
Correct.
Then
Understood.
only you will get a 0 vector, right?
Right.
If they are in perpendicular direction, they cannot belong to that space.
Correct.
Okay. So in that sense, so we have seen that if you remember this diagram correctly, so this is a 90 degree. So this is a row space of A. We have in the m dimension. So this is a null space of A transpose. And so this is a column space of A. And this is your null space of A. So here we have in the dimension m or n. So this is 90 degree. So therefore every vector, yeah.
Is the diagram correct? I mean, row space of A should be orthogonal to null space of A, right?
Null space of A, yeah, correct. Okay. Thank you so much. So this row space of A is every vector, if you consider, so we have solved some examples also. So if you take the vector span of any matrix in the R of A, and if you find the dot product with this N of A, you will get a 0. So that is how you can verify this orthogonality between the subspaces. Okay. So I hope it is clear how these two subspaces are orthogonal to each other. And one more thing is when, yeah.
The word orthogonal and orthogonal complement are one and the same, right?
Yeah, they are same in the sense orthogonal is we are getting the two vectors or we are taking the dot products as 0. Orthogonal complement is, see, R of A and N of A are orthogonal complements. So the vectors in R of A is orthogonal to the vectors in N of A. At that time, we call them as complement of each other. Complement means we have, we cannot say this R of A and N of A are orthogonal complements. When you mention them as complement, for every vector in R of A, there is an orthogonal vector in N of A. So likewise, so then only we call them as orthogonal complement.
So
Subspaces are
the
called as
number of
orthogonal complements.
ma'am, so the number of vectors should be equal in both the subspaces.
May not be equal. Yeah. The number of elements in the vectors should be equal.
Oh yeah, number of elements in the vector should be equal.
Yeah. So here we can have 3 vectors. Here we can have 2 vectors. You can check for the orthogonality between each pair. So that's why we call them as orthogonal complements. Similarly, it holds for the C of A and N of A transpose. Is it clear? Okay. So that's about our second lecture. So we'll move on quickly to the projections lecture. So here, so a system of equations Ax equal to B is inconsistent if, so a system is said to be inconsistent when it does not have any solution to satisfy the system. So then we call that system to be inconsistent. So when that condition occurs, when the B is not belonging to the column space of A. So when B belongs to column space of A, it's a consistent system. Ax equal to B has a solution. Second question, the column space of the projection matrix of a vector V is a line passing through V. So this is, I have made an application. Let me open it. So to illustrate the idea behind the projection matrix of vectors, see for example, so I hope this is visible to everyone. So the consider a vector V. So this V is 1, 1, 1. So for this vector, if you find the projection matrix, it will give you 3 by 3 matrix with every element equal to 1 by 3. So when you find the column space of that projection matrix, it is a single vector which is 1 by 3, 1 by 3 and 1 by 3. So this is the column space of the, the vector, which is, I'll write here. Okay. So I am having a vector V which is equal to 1, 1, 1. So for this vector, we are going to find the projection matrix which is P. So this, according to the equation, projection matrix can be found by V into V transpose by V transpose into V. So when you do so, you will get every element as 1 by 3, 1 by 3, 1 by 3. A 3 cross 3 matrix you will get. So for this projection matrix, I'm going to find its column space. So the column space of this projection matrix. So how we will do, we will reduce this matrix into its echelon form. So at that time, when you, this is your pivot element, when you go for reducing these 2 rows beneath the pivot element, you will simply get your second row minus your first row and the third row minus your first row, which will lead to all zeros here. So this is your only pivot element which belongs to the first column. So your column space of this projection matrix is a vector, that is a span of this vector. Okay. So this is your column space. So this column space, when you plot in a 3-dimensional space, it is a line. So that is this line. So your column space is 0.33, 0.33, 0.33. So this column space, when I multiply it with a vector V, so it is passing through this line. So that's why we have the option, the column space of the projection matrix of a vector V is a line passing through this V. So I hope you understood how we obtain this. So that's why it is a line passing through V. Okay. Next, consider the following statements regarding a projection matrix P. So we all know projection matrix, the square of the projection matrix is equal to the projection matrix itself, and the matrix is symmetric matrix. So just now we obtained the projection matrix. It is a symmetric matrix. Even though we have various values for V, you will obtain the symmetric. That is symmetric with respect to this diagonal. So your options 1 and 2 are correct, and 2 and 3 are 3 and 4 are false. So the null space of the projection matrix of a vector P. So let us return back to the first calculation here. So here we have considered the same vector. So for this vector, we have obtained the column space of this vector as a line passing through V. So how we have to find the null space of this vector? So from this reduced form, I can see that we have to find the solutions of this equation. That is the vectors which lead to Ax equal to Ax equal to 0. So at that time, you will get 1 by 3, 1 by 3, 1 by 3, 0, 0, 0. Into, so here we have 3 number of columns. So x1, x2, x3 is equal to 0, 0, 0. So now we can identify our pivot entry here. So this is our pivot variable x1. So which makes x2 and x3 as free variables. So we can freely choose this x2 and x3. So let us set this to our basis entries. x2 equal to 1 and x3 is equal to 0. So if you do so, so the first equation is 1 by 3 x1. So plus 1 by 3 x2 plus 1 by 3 x3 is equal to 0. So which leads us here x2 is equal to 1 and x3 is equal to 0. So therefore 1 by 3 x1 plus 1 by 3 is equal to 0. So which leads us to x1 is equal to minus 1. So your first vector will be minus 1, 1 and a 0. So similarly what we will do, we will have x2 is equal to 0 and x3 is equal to 1. So at this case also, if you substitute in this formula, this 1 by 3 x1 plus again will 1 by 3 will be equal to 0. So this x1 will again be minus 1. So here your second vector will be minus 1, 0 and 1. So if you see here, you have two vectors that span your null space. So at that time, you can see the null space is a plane. Just a minute. So here you can see the null space vectors minus 1, 0, 1 and minus 1, 1, 0. So for these two vectors, you will get a plane for your null space. So this is your null space plane. So when you have this vector V, so when you plot this vector is orthogonal to this plane. So the null space of the projection matrix of this vector is a plane which is orthogonal to V. So this is our answer here. So this is a plane is our answer. So this plane is a orthogonal to this vector. So this is how we obtain this plane orthogonal to V. So I hope we can understand how we can get this projection matrix and their spaces computation.
Ma'am?
Yeah.
Is this like always like orthogonal?
Always like orthogonal in the sense, yeah, it will for any value. If you change, you can change the value for V and then you can get one projection matrix and you can find it for yourself. How this computation occurs. You can calculate these steps and you can find the two vectors for the null space and we can try plotting it. Then you will find that they are orthogonal.
Thank you, ma'am.
Okay. I will also give you some guidelines. So this is the way to calculate. How to find, you assume a matrix and then you assume a vector and then you try to calculate the null space and column space. Then it will definitely lead to a plane which is orthogonal to.
So ma'am, this projection matrix, like again, like is it a linear map or it is a operator?
It It's a linear multiplication because when you get a projection, P is projection matrix multiplied by the B vector, no?
Yeah.
P
So
is equal to DB.
correct. So that means my argument is like it is not an operator. The reason being, it is projecting something from a different space to another space, right? Like there are two vector space including this projection stuff, right? Like it takes the vectors from
No,
one vector space and project into another vector space.
it is considering a vector and you can relate to that. But for a vector in one space, I think.
See this P
Yeah.
is a matrix, right?
P is a matrix
Correct.
okay, which leads
So-
to the projection. Yeah, right.
Right. So that matrix is matrix represent some kind of a map, or it is a operator, based on from where it is taking the input and where it is sending the outputs. So whenever there is a map or operator, there are two vector spaces associated with it. So for this P, what are those two vector spaces?
So I could not correlate
Yes.
in your way, but in the projection matrix,
Ma'am,
it is
can I come in?
Yeah, I can.
Yeah, from my understanding, Rajiv, that projection is the operator like ax plus b, wherein a is an operator, right? Because you take one vector and project onto another. So what relation, what operator will actually get that input vector which you are projecting onto the other vector? It's like saying u going to v through a. So you are taking one vector, projecting it onto another vector through P. So that's an operator in that sense.
But
That's my
if we call,
understanding actually.
yeah, but if we call that as an operator, so the general definition of the operator is like it works like operator is a function which maps from V to V. But here,
U to
like
V,
projection, sorry.
Yes. Yeah, U to V, like you said, yes, U to V.
Correct, but that is the definition actually,
Right,
because
right.
like in linear algebra, that's where they define the operators.
Correct.
Like V to V is operator, and
Mhm.
if say for example V to U or U to V, then it is a linear map. Okay. Now if it is V to V,
Mhm.
in that case, say for example, we know P square equal to P, right?
Correct.
Yeah.
Because if it is an operator, then it cannot work only because you are on that same vector space and you are projecting. So whenever you are projecting on that same vector space, it will always be P.
Correct.
Yeah, that's what the that's how we attain P square equal to P. No, we are already projected onto
Correct.
that space,
So-
and once again, if we project, it is already in the same space.
Right. So so that means it is a linear map. So one vector space I can think of, say for example B and A. Okay, in that example, where Sat told like this is B vector and this is A vector. So the span of A could be one because we are projecting on the span of A, right?
Yeah, on the
Projecting B
column
on the
space
span of A.
Yeah.
So the target vector space may be the span of target vector space is the span of A. But what is the source vector space? That is anything, right?
The source vector space can be any vector space.
Any vector space, and which is not the A vector space.
It cannot. It may not be in a linear combination of this matrix vectors, column vectors.
Correct.
A.
Now
But
my
in that
question
case-
is,
Yes. Sure.
okay, go ahead.
Yeah, I was saying in that case, then the P matrix will itself change, right? If that is not A and we are projecting some other vector, then P itself will change, right?
That's my point is
Yeah.
that P is like when we are calculating this P, we are taking a vectors from A, span of A, okay,
Yeah.
and we are calculating A transpose is the A transpose by that equation, right?
Yeah.
From that we are calculating the projection matrix. If I change my B, then this projection matrix is it not going to be different?
I think there are two things here, Rajiv. The one is the projection of particular vector A, right? And then we bring in B, the projection of B on A, correct? So if A changes, obviously P also will change. Either way, B can take any value, B can be of any value. Based on that, their projection on A will change.
Yeah, so my point here is,
Yes.
say for example, B is in another vector space, okay?
Right.
Say that vector space, if that vector space itself changes, will not the projection change?
It should
Like
not,
this,
because A is not changing here. If A is changing, then projection is changing, right?
so that means you are saying
Yep.
it is kind of a map. Sorry.
Yeah, go ahead.
Just a minute. Abhinandan, you raised your hand. Can you please unmute and tell?
Yeah. See, I was saying P depends solely on the source vector A. You multiply any other vector with A and you get projection of that vector along A. Basically, you are finding component of that vector along A. So P depends on A solely, not on B.
Yeah, I get that.
That's the whole valid point.
Okay, so basically like the understanding is like B can belong to any of these vector space, only the projection component along A will be defined by this projection matrix only.
Yeah.
Yes.
B
Got
will
it.
simply take the component of other vector along A.
Correct. Yes. But the projection matrix will be same.
Yeah. For a given matrix, it will be same.
Correct. For a given vector. Yeah.
Yeah, for a given vector. Yeah.
Okay, understand that.
Okay, thank you. So this is how we obtain the projection matrix. So these two relations are same, A into A transpose, and A transpose A, which you will be getting at this squared length, that is norm of A square. So these two options are correct for your projection matrix. Okay. So let's move on to the least squares and projections. So here let's go quickly. So if I n-cross min matrix, so now we have seen many things on invertibility of this matrix. So all these conditions are true. As we saw earlier, this C of A belongs to Rn, R of A also belongs to Rn, and the rank is equal to n. Okay. And so consider Ax equal to B. So the projection matrix of A is in the identity matrix. So if your B belongs to the column space of A, this is your answer. So when the matrix B is in the column space of A, so when you multiply that projection matrix P with that of B, you will get the AX equation. So therefore, since it is an, we will get an identity matrix here. So that's why this matrix is when B belongs to C of E, you will get the identity matrix, and the inverse, that is when B belongs to the left null space, you will get a zero matrix. So which will lead to AX equal to A transpose X is equal to 0. So based on that relation, your value will be equal to 0 matrix. So therefore, this is the answer. So this we have seen many times. Here, consider the following statements regarding the projection matrix. So which are the true conditions here? Your transpose of the P matrix equal to P and P square is equal to P. So 1 and 3 are true here. So next is simple, which is an example for your least squares. This is based on your least square projections. So here, in your least squares method, we have considered theta as your parameter. So if you consider the line, the slope and intercept is theta. So the condition here is it will have a solution. So when will it have a solution? When the length between this A theta and B is equal to 0. So this is the condition when you want to have a solution. And when you are trying to obtain the solution, what we are aiming at, you are aiming to minimize this distance between your A multiplied by theta and your B vector. So that is why the least square solution is a system of linear equations which aims to minimize this length between A theta and B. And finally, the least square solutions to a system of linear equations is obtained when B is projected onto the column space of A. So these are very straightforward questions. So that's all about the activity questions. So let's quickly move on to the practice assignment. So the first question, what is the length of the vector? So the length of the vector is square root of 1 square plus 1 square plus minus 1 square, which is equal to 1.73. It's a direct formula substitution you will get. And similarly, the next question is the inner product of 103 vector and minus 124. So if you multiply the corresponding elements, you will get 11. So 1 into minus 1, so 0 into 2, 3 into 4, 12. So 12 minus 1, it is 11. The rank of the matrix A. So how we will find the rank of the matrix? We are going to reduce this matrix to its row echelon form. So at that time, you will get the rank is 2 here. So I hope you are all familiar with row reduction steps. So is there any need to solve this row reduction, or shall we proceed?
No.
No need, no. Okay, that's simple. Because if you reduce this row, you will get the last row as 0 with only 2 pivot elements here and here. So at that time, the rank is equal to 2. So based on that same row reduction, if you reduce this matrix, you will never get a 0 vector. So the rank is 3 here. And the fifth question is, can we span the entire 4-dimensional space using the 4 column vectors given in the following matrix? So the same logic you apply, and if you find the row reduction process, you will never reach a 0 row vector, which means you will have pivot elements in all the 4 entries. So what happens? Every individual column vector is a independent vector. So it will span the R4 space. So that is why it is a yes here. And next is yes.
It is same as the linear combination of all the column vectors. All the column vectors being linearly independent, right?
Yeah, it is the same as that.
All right, thank you.
Okay, thank you. And for this question also, you are going to find the rank of the matrix. So if you reduce this matrix, you will get 0 rows here for the last row. So your answer for this question is 2, because when you reduce this matrix, you will get all 0 vectors in this 2 rows in the bottom. So the rank is equal to 2. And once again, if you follow the same row reduction steps, here for this matrix, you cannot reduce this row further to a 0 row vector. So the rank is 3. And for this question, the rank of a 4x3 matrix is 2. So what is the dimension of its null space? So it is also simple. Your rank is given as 2. Your number of columns is 3. So therefore, your null space is n minus r, which is 3 minus 2, that is equal to 1. And which of the following represents the row space of this matrix? So for doing this computation, you have to reduce this matrix to its reduced row echelon form. So when you reduce to that form, you will get a matrix with first 2 rows as 1, 0, 9, 2, 0, 1, minus 3, 1, and 0, 0, 0. So this is your span.
Yeah.
Yes?
Yes, so for this question, actually I got the answer, the first one, but the first one is not in terms of vector elements there. It's not exactly what we get from our from row echelon, reduced row echelon form.
Yeah.
What we get is something different, but this is a linear. That's a linear combination of these two. That's what we get.
Yes.
We are not getting exactly these two vectors.
You're not getting okay.
No, but it's a linear combination of these two.
It's a linear combination of these two.
Yeah, both the
so in
both
the
the
sense,
increase
how did
and
you
the
do?
nulls. So I calculated that based on the methods that we follow.
Maybe you would have taken that column space of A transpose.
No. I did everything like we do and the process that we have. So we first of all we make it in the form of row reduced echelon form, right? And
okay,
then we take.
How did you get the row reduced echelon form?
I mean, we just remove the, we take the first column, first entry as pivot, and then perform row operations, right?
Okay.
So that's what we do. So final null space that I got
Okay.
was not exactly the same. But then when I tried to find out the linear combination of individual vectors here in the first answer, then I got
Okay.
my answer that they are connected. So that's why it should be the answer.
Okay, so you just moved from this step, but you didn't reach that row
I got
echelon
my
form.
own null space vectors, a span of null space. Sorry.
Okay,
Yeah.
okay. But
Row
that's
space.
simple.
I did the row
So,
space, right? We had to do this transpose first, right?
yeah, so there are two possibilities. That is, if you take this matrix A and if you
Mhm.
have transpose it and if you
Right.
find the column space,
Hmm.
that is the row space. But in doing so, you will get 2468 and 1305 as your
Correct. That's
span
what
of
I
them.
did. Yeah. So that's
That
the
you
span
might
of
have
these two.
obtained,
Yeah.
right?
Yes.
Yeah,
Yes.
yeah. Oh, okay. I got your point. So while
Right.
doing so, what happens is you are taking the same row vectors as the basis of your row space.
Mhm.
When you form this reduced row echelon form, what you are finding is you are finding a basis for the row space. So this basis is the unique solution. So that's why I have, even in my tutorial, I have showed that method for finding the row space using the reduced row echelon form.
Okay, so we have to go to reduce row echelon form, and
Yeah.
then therein we get. So yes, I got 2468 and 1305.
Yeah, that is what you might have got. Yeah, that
Right.
is the regular steps. That is the usual steps wherein you are
Yes.
taking this, you are considering this matrix as a transpose, and then you'll find the pivots,
Correct.
and correspondingly you will take the columns. That will give you 2468 and 1305.
So we have to go
In
to the
order
final
to,
reduced row echelon form, right? Not just row
yeah,
echelon form.
no. At that time, let me solve it for you.
Mhm.
So your matrix here is 2, 4, 6, 8, and 1305 and 1168. See, first in order to get a reduced row echelon form. So in reduced row echelon form, what happens? Only the pivot elements are equal to 1, and above and below you will get a 0. So if you look at here, the leading entry, this 2 is a non-zero number, which can be a pivot, but for reduced form, it has to be 1. So we have to do R1 divided by 2. You take this as a multiplier and then divide it by 2. So at that time, you will get 1, 2, 3, 4 and 1305 and 1168. So now you have a entry which is 1 here. So now we can reduce the bottom two rows, right? So we can go for R2 minus R1 and R3 minus R1. So now you will get 1, 2, 3, 4. So 1 minus 1, 0. 3 minus 2, it is 1. 0 minus 3. 0 minus 3, it is minus 3. 5 minus 4, it is 1. And here 1 minus 1, 0. 1 minus 2, it is minus 1. 6 minus 3, it is 3. 8 minus 4, 4. So like this, you have to reduce. So now I am reduced it, and now we can see this is the pivot element here, the second row, the second column. So now we can, so if you look at this entry here, so for this pivot column, pivot entry, the element beneath and above has to be equal to 0. But if you see here, this element is not equal to 0. So what I am going to do is, so before that, you can also make the top and bottom element 0. So R1 minus 2 here, R1 minus 2 R2. So what happens here? Bear with my handwriting. So 1 minus 0 is simply here 1. So 2 minus 2, it will be 0. So 3 minus of 2, so it is 9. And 4 minus 2, it is 2. So now you will get 0, 1, minus 3, 1. And for bottom row, what you can do, it is simply R3 minus R3 plus R2. So at that time, you will get 0, So here also 0. So here 0. And 4 minus 4. I think actually I have to get a 0 here. I made any mistake. So this is what happens. So if you do like this, you will get a reduced row echelon form, which is giving you this span. So why this span is important means in this reduced form, you will get a unique solution. Even before this 2, 4, 6, 8, you would have obtained. So these are also the linear combinations of this basis. So that is why they are basis for your row space. So it is a best practice to find the row space from the reduced row echelon form itself directly.
So when we do it this way, how does this relation come between calculation of rows, basis of row space through by transposing it, and or the other way is like you did, right? So where does this linear relationship of linear combination come from?
Because these from these two vectors here, you can reach the span of this row space.
Okay, we can
1, 1, 6,
reach
3.
to all
Yeah.
right, that's right. So in this regard, ma'am, I have just one submission. I think there is a similar question in graded assignment also. I'll not go to the answers and all. But what I'd like to submit is that the span I get there using the same method consists of just one vector, right? While the answers are all having two vectors, and one of them is actually one element of one of the answers is actually matching with what I there. So why is that happening? I should also get through the other method also. I should get at least two vectors.
I don't know.
There is one question, right? Using
which
similar method in graded
question?
assignment. In the graded assignment, I think the last question it is, we are calculating the same thing, I suppose. But there, I guess it's a null space. It's a null space, I guess.
Okay.
In the graded assignment now.
Okay, in the graded assignment.
No, I'm not asking you to give me the answer. I'm just telling you that I got an answer which has just one element in the span, but all the answers are having two elements. But one of the elements that I have derived is actually part of one of the answers. So I
you're
not understand.
you're not getting the part of the answer, right?
Right. So there are two vectors in the answer. I got only one.
But in the graded assignment, we have only that.
Could you just see the answer if it is possible? I mean, the question, just that. Just the question, not discuss the answers.
See there we. Abhinandan, can you comment on it?
Prashant, we cannot comment as of
Disclose.
now.
Okay, no problem.
But null space of the matrix, for finding that, you can easily find from no need to go to that reduced row echelon form. Simply from that.
We have to do the echelon, right?
You have to reach that upper triangular form. That is U.
You have to do
that
AX
is
equal
enough.
to 0. AX equal to 0. That's it.
Which I showed for finding that.
Yes.
I showed you for plot with respect to V. I found the null space for that projection matrix. The similar steps you have to do. Then you will reach.
Yes, I understood this one. Thank you. Thank you so much. Yeah.
Null space.
Yes.
Okay, but I'll also cross check any changes are needed. We'll make it. Okay. Thanks for actually informing. I'll check for that question whether answers are there.
Thank you, ma'am.
So I hope you understood how we form this one, and find the projection matrix for V. So it is very simple. It's just I already provided in our lectures. So we have to find V transpose V by V into V transpose. When you do so, this is the matrix you will get 1 by 3, 1 by 3, all 1 by 3. And finally, find the projection of the vector along the another vector. So for this projection, if you find, so let me calculate. So if you find the projection of that vector, so we have that vector U. I think projection is simple. So let us take this vector U as 1, -4. comma 2. So I'm going to project this vector along the another vector v that is equal to 1 comma minus 2 comma minus 3. So when you have this projection formula, it is simple. It is just v transpose u by v transpose v. See, actually in the question, we should have mentioned this is a transpose, because normally we make a vector to be a column vector. So then only we can substitute in this formula here. So when you find this v transpose into u, so that is this vector and the dot product with this vector. So that is equal to, you will get 3 here. That is 1 into 1, 1 minus 2 into minus 4, that is 8, 1 plus 8 minus 6, that is equal to 9 minus 3, that is 3. And divided by this v transpose v, which is a dot product of this vector with itself. So which is 1 plus 4 plus 9, so that is equal to 14. And you are multiplying this vector with v vector. So therefore 1 comma minus 2 comma minus 3. So which is 3 by 14 minus 6 by 14 and minus 9 by 14. So that's your answer. So previously it was mentioned wrongly that we have now changed the option. So this is your correct option. 3 by 14 minus 6 by 14 and minus 9 by 14. So that's all with our activity and practice for week 3. So if you have any general queries on this, any of these assignments, you can ask. In any of the week 3 contents.
Ma'am,
Yeah.
I mean, are the solutions, the options for the graded assignment, are like all of them are correct, or are there any mistakes?
No, actually, in the discourse forum, we have mentioned 2 options for that questions that we will not consider. You can kindly refer to that discussion forum where the projection question.
11 and 13, I guess, right?
Yeah. So we will post an announcement so that it will not affect your grading.
Okay, ma'am.
Some minor typos. So we are extremely sorry for that. We'll make sure we'll never do that again.
Okay, ma'am. Thank you.
Okay.
Ma'am,
So, ma'am, this
yes, sure. Go ahead, Raj.
Yeah. Yes, Rajiv.
okay. I was asking like this, like quiz 1, you will be till week 4, right?
Quiz 1,
Yes,
yes,
it will
it will
contain
be
1 to 4 contents. Week
1
1
to
to
4.
week 4. Yeah.
And like what is in week 4, like because earlier I saw that in that like home page, right? Like week 3 was eigenvalues, eigenvectors.
Yeah,
And
this is coming in week 4. Contents are a little bit shuffled, but you are going to
okay,
get that in week 4 now.
okay. So week 4, is it eigenvalues?
Yeah,
Yes.
eigenvalues and eigenvectors are there.
Okay, okay.
It will be released soon.
Hopefully,
Okay,
this
thanks.
Friday we'll release the contents for week 4.
Ma'am?
For week 4, I think by this Friday we'll release week 4 contents, right? Every Friday you will get new contents released.
Yes, yes.
Ma'am, the eigenvalues and eigenvectors, will they be taught from the beginning, or I need to go back and learn the basics and foundation?
No, it will be taught from
Sure.
beginning.
Yeah, it will be taught from beginning. You will be taught to how to calculate the vectors and some diagonalization of the matrices will be there.
Thank you, ma'am.
You don't have to brush up any topics. Sir will teach from the basics.
Okay, ma'am.
Questions for quizzes. I mean, quiz 1. Can we expect in the same line of graded assignments, or will it be like a little bit more complicated and difficult?
It's a
Yeah,
related question. You may expect difficult questions then.
Right, because one of the reasons why I see not many people coming to these sessions are maybe they're finding it very easy. I don't know, no, I don't find it easy, but many of them. So if quizzes are going to be along the same line, then at least for me there is not much to worry about. Just my
Some level of
assessment.
difficulty,
Yeah,
some
yeah,
level of difficulty, some increased level of difficulty, not the
yeah.
same kind.
Thank you. Ma'am. Just one more question
Because, yeah.
about graded assignment one. The one correction that you had said will be made. So our scores are out. So does that score already account for the corrections that you're going to make, or it is still to come?
See, I will have to ask the team members, but they have considered this reevaluation and grading. Your score right now should be with those changes incorporated. But for anyway, we'll cross check. But to my knowledge, they have incorporated the changes we have mentioned.
Ma'am, will they be reflected? I mean, the options will be corrected or correct options will be updated in the questions in the future?
You're asking about the week 3, yeah? Third week.
Whatever the typos are there, will they be corrected?
No,
And
for the week 3, it will not be corrected. It will be the same.
in the
Yeah,
past
just
weeks?
for the past weeks, the option ranges will be changed. There are no corrections in the options, right? The past weeks, the range was not accepting your answer.
Oh, for
And
example,
for week 2, we are changing. Yeah,
a
let me complete.
question. Okay.
Yeah. Just a minute. I'll clarify you. For week 1, actually, there were 2 re-evaluations, but for those who we are reconsidering the options, and those who have marked it correctly will get correct answers. For week 1, only the range is different, so it will be ignored in one question. Do you agree with me, or do you have any points other than that?
I mean, I generally what I do is whatever wrong questions I got, I
Okay.
take those questions and pile up and I work on them. But some
Okay.
of the questions, like I got it right, but the options were wrong. So
Okay.
if those were updated in the future, I can like simply check answers and see that I answered them right. That's my concern, not the marks.
Yeah, it will be updated. That's what I'm telling you. For the second week, will be, for example, that one question with the line value 786 plus alpha into 123. For that question, we are giving the marks for the correct answer. If you look at the previously, before making corrections, it will be chosen as a wrong option, but now it will be chosen as the correct option.
All
So
right.
we have changed the correct options in the portal also.
Okay, and
For
also
week 1 and week 2.
Okay.
But the scenario for week 3 is, since for week 3 deadline is yet to come, we could not change the option. So once the deadline is over, we will provide you the, we will ignore that question and then we will change the options. That will happen after the deadline is over. So finally, in the final output after this week 3, you will get the correct options in the question, but it will not be used for grading since there were mistakes earlier.
All right, ma'am. Thank you. I got the answer.
Okay.
In general, week 3, what I felt was activity questions were difficult and practice and graded assignment questions were easy.
Okay.
Because practice assignment questions and graded questions were completely like computational part.
Okay.
So when you know the procedure and everything, when you know the formula, you can do it. But I'm not, I mean, I got many wrong. I answered wrong in a lot of activity questions because of, and most of them were conceptual.
Yeah.
So when it,
yeah, you go ahead.
Yeah, so when it comes to the quizzes, will this be like in the quizzes, there will be combination of conceptual questions as well as the computational questions, or will there be anything different than what we have seen in the practice assignment, graded assignment, and activity questions?
Yeah, you can expect a mixture of all these three. There will be some you can expect some conceptual as well as this kind of direct computation of the formulas. It's a combination of all the three. We maintain a level of difficulty. Based on that, we set up the questions. So since in our machine learning foundations, we are dealing with the introduction part in the basic 2 weeks. So only we think the content may be easy for you or like that. But questions from the week 3 will be having both the conceptual wise questions and also this numerical answer type questions. You can expect both.
Okay, thank you, ma'am.
So if there are no more questions, then shall we close the session?
Yeah, so I'm just last question, like we have another session on Saturday, right?
Yeah, even no, tomorrow we have that solve with this session.
Okay, tomorrow we
And
have.
on Saturday we have an open session.
Yeah.
2 more sessions we have.
2 more session for week 3, right?
Tomorrow basically we will solve some 2 more sessions for week 3.
Okay.
Tomorrow I plan we'll solve some questions, some conceptual questions, and as well as some similar kind of the computation of the problems related to projections.
Yes.
And least squares like that I have.
Yeah, probably like if we can come up with some kind of like least square, a little bit trickier questions, right?
Yeah.
So that will be good, because like we found there was only one or two least square questions. Okay, so if you possibly like in the like tomorrow or day after tomorrow, if you can like because you have already like solved up to this practice assignment, right?
Yes.
So already these things are covered today. Graded assignments we are not going to discuss, right? So basically essentially like you need to discuss some like new problems, right? Yeah, and probably like if we have some conceptual doubts, like conceptual doubts.
Yeah.
Correct. So if you can provide some more exercises on this this regression, right? Like least square.
Yeah,
So
least squares. I've taken 2 problems regarding to that least squares.
Yeah. Or like if there are some tricky questions, like say for example, like now it is like a little bit simpler, right?
Yeah.
Like there are only 2-3 steps. So if there are some other type of questions like that, it is not very explicitly mentioned that go and find out least squares, but eventually we need to end up computing least squares. So that kind of questions, like if you can give us some idea, that will be
okay. Yeah, definitely. I'll give it a try.
Okay,
ma'am.
thank you.
Yeah.
We have seen the solving least squares using only one dimension. So why have we not seen any like some tutorial or solving 2-dimensional problems?
It is coming next week.
It's coming in next week.
Yeah, I mean second degree polynomial fit is coming next week.
Yeah.
Okay, thank you.
In the upcoming weeks, yeah, you will learn.
Hello, ma'am. Yeah,
And
just
also,
yeah, sure.
Yeah. So in machine learning foundations, we mainly focus on making the concepts clear so that it will be easy for you when you go for the machine learning techniques and machine learning practice. So there you will not be solving such problems based on the basics. So in order to work with some high dimensional data, we are needing for this background knowledge. So that's why we have made it clear so that you will understand if we tell any concept there, okay, we have studied in our MLF. So that's the reason why we place a strong foot on this fundamentals. You can see some applications related to that eigenvectors in the coming weeks. So where we are going to apply such matrices.
Okay, ma'am. Thank you for the information.
Okay.
Ma'am, can you check one thing? That's my suggestion. Under the supplementary contents, where you have given link for YouTube live sessions. So I clicked on one of them. I ended up in Math 1
That's
live session YouTube
Yeah.
link. So
Yeah.
yes, I ended up in Math 1. I don't know how.
We'll check.
Yeah, please just have a look at that.
Prashant,
Yes.
Okay.
in that document, there are tabs. So the first tab is a default tab, which is Maths 1. There is a MLF tab. If you click on that, you will see the links.
Okay,
for
everything is
Okay.
consolidated, I guess, you're right, from different
Yeah.
subjects. Oh,
Yes.
okay, that may be the problem from my side, because usually in previous trimesters, I mean, they would have for separate subjects, separate links, right?
So here you have
That's
to
what
go
I
to
confused.
MLF, right?
Yes. Okay, there are okay. That's my bad, ma'am. Sorry.
Okay.
I just could not.
So I
see.
thought that this YouTube link itself is leading to Max 1.
Right, I understand that now. Thank you very much. Thank you, ma'am.
Thank you for clarifying that. Okay, so we'll meet tomorrow for that solve with the session.
Yes, ma'am.
So thank you all for your participation and for your insights.
Thank you, ma'am.
Thank you very much.
Thank you, ma'am. Good night.
Thank you.
Thank you all.
Thank you all. Okay. Thanks, Abhinandan.
Yeah, ma'am.
We can
Ma'am.
stop the live. Vignesh is there? Vignesh, are you there?
Hello. Yes.
Hello?
Yeah.
Yeah, the session is over. Vignesh.
Okay,
You can
okay.
pass them.
Okay. Thank you. Yeah.